Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, in this course, I will deliver my lecture on Waard classification for Granulites Part 1. I will cover this topic in two parts. In Part 1, I will proceed under the following heads: Introduction and Waard classification for granulite facies and summary. Hope it will be useful for you. On the basis of pressure and temperature, we can divide the metamorphic facies into three types, mainly: 1. Facies of low pressure, 2. Facies of intermediate pressure, and 3. Facies of higher pressure. Mayasiro originally recognized three different facies series. Number 1, a geolite, prehenite, pumpelite, blue schist, eclogite type. Number 2, a typical Barrovian type characterized by green schist, epidote amphibolite, granulite type characterized by paragenesis of kyanite, sillimanite type. And number 3, an Abukama type of green schist, amphibolite, granulite characterized by paragenesis of andalusite, sillimanite type. The facies of intermediate pressure or Barrovian type are listed on the screen in order of increasing temperature and pressure of metamorphism: A. Geolite facies, B. green schist facies, C. amphibolite facies, D. granulite facies. The granulite facies are described by Ascola in 1939, is based on the ideal assemblages in which micas and amphiboles are no more stable. The rock of this facies belong to the very high rank of metamorphites, in which muscovite is no longer stable, and consequently potash feldspar coexists with aluminosilicate polymorph sillimanite. Moreover, in rocks of suitable bulk composition, orthorhombic pyroxene characteristically appear in place of anthophyllite, gaderite or cummingtonite. The paragenesis of impure calcareous rock is similar to the amphibolite facies, the granulite facies rock in the deep-seated zones and now represented in Archean crystalline complex of the continental shield. For example, South India granulite terrain of the Indian shield. In anhydrous peltic composition, feldspar, sillimanite, almandine, cordierite and hypersthene are common assemblages. In basic assemblages, both orthopyroxene and clinopyroxene with plagioclase are found. Winkler 1976 called the granulite facies as a regional hypersthene zone because the diagnostic minerals hypersthene present in both peltic and basic paragenesis. Waard in 1965 proposed a six-fold classification of the granulite facies depending on the high, intermediate and low pressure peat load. Each divides further by the presence or absence of OH bearing minerals, mainly hornblende biotite. Two subfacies of relatively high load pressure are characterized by clinopyroxene almandine and two intermediate subfacies by orthopyroxene plagioclase and two subfaces of relatively low load pressure by cordierite almandine assemblage. Of these six subfaces, the three with relatively high water vapor pressure contain hornblende and biotite, in addition to characteristic anhydrous assemblages of the three subfaces of relatively low water vapor pressure. First, hornblende orthopyroxene plagioclase granulite subfaces are plagioclase granulite subfaces of Waard corresponds, and orthopyroxene hornblende granulite and pyroxene subphases mentioned above, the assemblages orthopyroxene plus plagioclase characteristic of the above subphases because unstable if the pressure exceed a particular value of a constant temperature. The two minerals react each other from clinopyroxene almandine pyroxene granulates by the following reaction. Orthopyroxene plus plagioclase give rise to clinopyroxene plus garnet plus quartz. This reaction has been investigated by Green and Ringwood 1967, who obtained equilibrium conditions of the reaction at about 700 degree centigrade between 8 to 10 kilobar. Though this reaction, therefore, the pair orthopyroxene plagioclase is replaced by the pair clinopyroxene plus garnet, and thus plagioclase now coexists with clinopyroxene and garnet. This is the of clinopyroxene almandine granulite subphases. This is entirely devoid of hornblende and biotite. The corresponding subphases at higher PS2 are hornblende, clinopyroxene, almandine, granulite subphases. The peltic calcareous assemblages is similar as hornblende, orthopyroxene plagioclase and orthopyroxene plagioclase granulite subphases. The cordierite almandine subphases occupies relatively low load pressure region of the granulite facies environment. This facies is thus transition between orthopyroxene plagioclase subphases and pyroxene hornblende subphases at higher and lower pressure respectively. The corresponding subphases at relatively higher P water cordierite almandine biotite subphases form. The typical peltic assemblages are number 6 cordierite almandine subphases. First, cordierite, garnet, hypersthene, potash feldspar, quartz, plagioclase. Second, cordierite, garnet, sillimanite, cordierite almandine biotite subphases. Third, cordierite, garnet, hypersthene, biotite, plagioclase. Fourth, cordierite, almandine, sillimanite, biotite, plagioclase. The basic and calcareous assemblages are similar to orthopyroxene plagioclase and hornblende pyroxene plagioclase subphases. There are several reactions proposed for the appearance of cordierite in these subphases. Reaction almandine plus biotite give rise to cordierite plus hypersthene plus potash feldspar plus water. Second, biotite plus sillimanite plus quartz give rise to cordierite plus minus almandine plus potash feldspar plus water. Another reaction is biotite plus quartz give rise to cordierite plus almandine plus orthopyroxene plus potash feldspar plus water. Hornblende orthopyroxene plagioclase subphases. On the basis of ACF, AKF and A-F-M' diagram, the following assemblages are observed. Here every assemblage is same except a small amount of hornblende and biotite present. Important reaction occur within this subphases and hornblende orthopyroxene plagioclase subphases change in orthopyroxene plagioclase subphases. Hornblende plus quartz react and form orthopyroxene plus clinopyroxene plus water. Hornblende plus almandine plus quartz give rise to orthopyroxene plus plagioclase plus water. Anthophyllite give rise to orthopyroxene plus quartz plus water. Fourth, orthopyroxene plagioclase subphases. Charnockite, typical charnockite without garnet. Basic rocks, plagioclase, diopside, orthopyroxene, potash feldspar and quartz. Calcareous assemblages, plagioclase, diopside, gracilurite, potash feldspar plus minus quartz. Number 6, calcite, diopside, gracilurite, potash feldspar plus minus quartz. Ultra basic assemblages, diopside, orthopyroxene, potash feldspar plus minus quartz. The reaction take place at the junction of these two subphases. Biotite plus quartz give rise to orthopyroxene plus garnet plus potash feldspar plus water. Another reaction is biotite plus sillimanite plus quartz give rise to almandine plus potash feldspar plus water. Higher pressure site, hornblende, clinopyroxene, almandine subphases. One can see the assemblage with the help of ACF, AKF and A-F-M- diagram, reaction orthopyroxene plus plagioclase give rise to garnet plus clinopyroxene plus quartz. Number 2, clinopyroxene garnet subphases. If we will see the ACF, AKF and A-F-M- diagram, we can observe that peltic, calcareous and ultramafic minerals assemblages are same, only change in basic assemblages. The basic assemblages is clinopyroxene garnet plagioclase quartz. Number 4, cordierite almandine biotite subphases. Here one new minerals appear first time, that is cordierite. With the help of ACF, AKF and A-F-M- diagram, we can observe different assemblages. Important reaction in this subphases occur and cordierite almandine biotite subphases change into cordierite almandine subphases. Biotite plus sillimanite plus quartz give rise to cordierite plus garnet plus potash feldspar plus water. Another reaction is biotite plus sillimanite plus quartz give rise to cordierite plus potash feldspar plus water. And another same reaction product is your cordierite plus garnet plus water. Fifth, cordierite almandine subphases. On the basis of ACF, AKF, A-F-M- diagram, we can observe different assemblages. The basic calcareous and ultramafic assemblages are same as in orthopyroxene plagioclase and orthopyroxene plagioclase hornblende subphases. The only difference is in peltic assemblages. Peltic assemblages, first garnet, cordierite, sillimanite, potash feldspar quartz. Second, orthopyroxene, garnet, cordierite, potash feldspar quartz. While anhydrous in nature, no biotite is present in peltic rocks. If biotite present, then cordierite almandine biotite subphases. All assemblages are same where Fe-rich biotite plus quartz give rise to garnet plus cordierite plus orthopyroxene plus potash feldspar plus water. When Mg biotite plus quartz give rise to orthopyroxene plus cordierite plus potash feldspar plus water. Biotite plus garnet plus quartz give rise to cordierite plus orthopyroxene plus potash feldspar plus water. Granulite subphases, CO2 present in cordierite, no H2O in structure formula, half H2O and CO2. Phi and Turner 1966 and Turner 1968 do not recognize any subphases, but they do recognize amphibolite granulite transition phases, which may be taken to correspond to the hornblende orthopyroxene plagioclase granulite subphases of Waard 1965. The hornblende orthopyroxene plagioclase granulite subphases and orthopyroxene plagioclase granulite surfaces of intermediate P load of Waard correspond to the hornblende granulite faces and pyroxene granulite faces of Turner and Barugan 1962. Dear student, today in this lecture we have discussed about the Waard classification part 1. I have covered this topic under the following heads: Waard classification for granulites. I believed this lecture was useful for you. In my next lecture, I will cover pressure temperature condition of metamorphism during granulite phases. For further studies, please read the textbooks, references and links given in the text. Thank you very much. For further studies, please read the textbook, references and links given in the text. Thank you very much. Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, in this course, I will deliver my lecture on Dewar classification for Granulite facies part 2. In this lecture, I will proceed under the following heads: PT condition of metamorphism during Granulite facies and summary. Hope it will be useful for you. Try to be regular in course. In some region, successive zones characterized respectively by amphibolite facies, the hornblende Granulite subfacies, hornblende orthopyroxene plagioclase subfacies, and pyroxene Granulite subfacies, orthopyroxene plagioclase subfacies constitute a progressive sequence of advancing metamorphic grade. Elsewhere, again there is a textural evidence in the form of corona and other replacement structures that pyroxene Granulite assemblages are in process of retrogressive metamorphism to hornblende Granulites or amphibolite facies assemblages. These field and textural relationships are constant, with widely preventing view that the Granulite facies represent high temperature of metamorphism. The temperature is of the order of 700 to 750 degrees centigrade to 850 degrees centigrade, as shown by the reaction biotite plus sillimanite plus quartz give rise to garnet plus cordierite plus quartz plus S2O 700 degrees centigrade 2 to 5 kilobar. Mg anthophyllite give rise to orthopyroxene plus quartz plus water 745 degrees centigrade 1 kilobar, carried out by Greenwood 1963. Muscovite plus quartz give rise to potash feldspar plus sillimanite plus water 662 degrees centigrade 3 kilobar by Day 1973. These reaction biotite plus sillimanite plus quartz give rise to cordierite plus minus garnet plus potash feldspar plus water has been studied experimentally by Holdaway and Lee 1977, and the equilibrium condition of reaction are 700 to 750 degrees centigrade between 4 to 8 kilobar. The reaction is already complete in upper part of the amphibolite facies. Mg anthophyllite give rise to orthopyroxene plus quartz plus water. Mg xmg equal to 0.6 775 degrees centigrade 6 kilobar, 680 degrees centigrade 5 kilobar. When xmg equal to 0.8 775 degrees centigrade 6 kilobar, 720 degrees centigrade 5 kilobar. The above two reactions Mg Fe anthophyllite investigated by Dewar and Henrichsen in 1975. They also studied the above reaction in the natural anorthite and synthetic one and found the breakdown temperature as 835 degrees centigrade 6 kilobar and 750 degrees centigrade 5 kilobar. MgFe gedrite plus quartz give rise to cordierite plus hypersthene plus water 755 degrees centigrade 2 kilobar, 705 degrees centigrade 1 kilobar. The reaction was carried out by Winkler 1966. Partial melting of amphibolite through the reaction hornblende plus quartz give rise to orthopyroxene plus clinopyroxene plus plagioclase. The reaction occurred between 700 to 750 degrees centigrade at 4 to 10 kilobar beans in 1969. It seems likely that the Granulite facies pass a considerable range of pressure of kyanite almandine rich composition of hypersthene and the pyro-rich garnet are believed to be reflect high pressure condition of their formation. The association of clinopyroxene plus almandine plus plagioclase also indicate a pressure of 8 to 10 kilobar at about 700 degrees centigrade. As already mentioned above, on the other hand, pressure of sillimanite plus cordierite in some granulite suggests that these are formed at relatively lower pressure, maybe as low as 7 kilobar. Furthermore, the pyroxene granulite facies rocks are essentially dry or anhydrous, suggesting very effect on reaction, including the transformation of hydroxyl bearing minerals into anhydrous ores. Of example, Henrichsen in 1975 has shown experimentally that the breakdown of reaction of hornblende, one natural and two synthetic, occurs in temperature range from 850 degrees centigrade to 1020 degrees centigrade at 1 kilobar P water, where P water equal to P total. These temperatures are not reached in regional metamorphism. On the other hand, lowering of P water relative to P total, that is P water less than P total, decrease the reaction temperature at constant P total, can be realized only in the deeper part of the crust where very little water had occurred in igneous rocks and to metamorphosed sedimentary which has lost most of their water either during an experimentally long period of regional metamorphism or during previous period of high grade metamorphism. In many areas, granulite facies of rocks are polymetamorphic, and these facies of rocks are restricted to Precambrian. Dear student, today in this lecture we have discussed about the Waard classification for granulite part 2. I have covered this topic under the following heads: pressure temperature condition during Waard classification and summary. Thus, on the basis of the detailed studies of different subfaces and also with the support of experimental data, we can conclude that during granulite facies the temperature varies between 700 to 750 degrees centigrade to 850 degrees centigrade and pressure in range of 6 to 10 kilobar. I believe this lecture was useful for you for further studies. Please read the textbooks, references and links given in the text. Thank you very much.